Welcome to MRS Bulletin's Materials News podcast, providing breakthrough news and interviews with researchers on hot topics in materials research. My name is Laura Lay. Much of the research into improving solar cells has so far concentrated on perovskites and organic materials. A smaller body of research shows promise for one of the oldest studied photovoltaic materials, selenium. Recent work has uncovered a tandem solar cell architecture that can be constructed by depositing the top cell directly onto the bottom cell.
Selenium seems to be very, very easy to get going very quickly without optimizing an awful lot. And I think that holds some really great prospects. I think it's a very exciting time to be studying selenium indeed.
That was Dr. Rasmus Nielsen from the Technical University of Denmark. Although previous research into selenium solar cells led to optimization of a single junction architecture, it's not as simple as layering this on top of silicon.
The device architecture that had been optimized by IBM researchers in 2017 was actually not transferable to a tandem, because as soon as we had to either invert the device architecture or just introduce transparent electrodes instead of gold, the energy band alignment turned out to be quite severe and we got transport issues.
Selenium-based single-junction solar cells have traditionally used fluorine-doped tin oxide. In this work, indium tin oxide was used as the transparent conductive layer, which is easy to deposit and its use is more widespread. Dr. Nielsen's team fabricated the entire tandem cell in-house, including the silicon solar cell. This allowed them to alter the device architecture, for example by changing the thickness of the carrier selective contacts in the silicon solar cell, which protects the silicon layer from the processes used to deposit subsequent layers on top. This allowed the top cell to be deposited directly and, since the selenium can be deposited at low temperature, this leads to an efficient monolithic construction process. So the selenium forms the top cell of the tandem device, with silicon used as the bottom cell. Initially, a zinc magnesium oxide layer was used as the N-type contact on the bottom of the selenium-based top cell to maximize the voltage, which led to an open circuit voltage for the tandem cell of almost 1.7 volts. The downside of using zinc magnesium oxide was that a critical transport barrier restricted the flow of electrons. Replacing this material with titanium reduced the barrier height, but led to a lower open circuit voltage, suggesting there is more work to do.
What I hoped to get out of actually doing this was to being able to outline the main challenges that needed to be overcome.
Selenium is prone to defects, but despite this, still demonstrates good performance.
Even though we have a lot of defects currently in selenium and we're trying to figure out exactly whether they're point defects or extended defects, it seems as if our current collection is actually remarkably good. And I think that's puzzling and at the same time very, very interesting.
This research shows that, before efforts focus on defect engineering, attention should be paid to the substrates used to grow the solar cell layers. Consideration should also be given to including surface modification layers. There are a few research papers on selenium compared to other candidates for solar cells, but despite this, the efficiency of selenium-based solar cells has improved dramatically. Further research could continue to improve their efficiency and demonstrate longevity. This research also demonstrates that it could be easy for other research groups to get involved.
The selenium is quite simple to fabricate, so it's maybe even low capital cost for a research lab. Considering how few groups are doing it right now, I think there's a lot of low-hanging fruits to be picked in terms of improving performance, improving efficiency, and also just to study some of the most fundamental properties of the semiconductor. Even though it's been around for 200 years, there are a lot of unanswered questions.
This work was published in a recent issue of PRX Energy. My name is Laura Lay from the Materials Research Society. For more news, log on to the MRS Bulletin website at mrsbulletin.org. Follow us on Twitter at MRS Bulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.